Hi everyone. In this video I'm going to walk you through an example using latent growth curve modeling with R, and we're going to be carrying out our analysis with the Latent package. So this demo is based on the second example in chapter 14 of Schumacher and Lomax's 2016 book, A Beginner's Guide to Structural Equation Modeling, 4th edition. And in this example, the authors modeled change over time in cell phone customers' levels of satisfaction. So they basically have repeated measures of reported satisfaction, basically 4 time points. And then there's also a between subjects factor, which is gender, and that is coded 0 for female and 1 for male. So unfortunately, there appears to be a small syntax error in the text that results in incorrect output, and ultimately impacts the interpretation of the model parameters concerning the effect of gender on this person-specific intercepts and slopes. So this particular presentation is not aimed as a critique per se. It's mainly just a walkthrough of the analyses, but using the corrected version of the syntax. So if you want to obtain a copy of the text file with the syntax that's used in the walkthroughs, you can go to this link right here. You can also download a copy of the R data file that I'm going to be working from right here. So I will also include these links as well as a link to this PowerPoint underneath the video description. So let's look at their example in the chapter. So this is it right here. It's drawn out. It's the latent growth curve modeling. They drew it out using the AMOS program, but we can walk through it and just kind of talk about the different components. So first off, you'll notice that over here we have 4 measurement occasions. You can think about it as basically time 1, time 2, time 3, and time 4, and these are the repeated measures with respect to customer satisfaction. You'll notice that all 4 of these repeated measurements are loaded onto 2 latent factors. So you have an intercept factor and you have a slope factor right here. And you'll notice that the factor loadings from the intercept factor to the repeated measurements, they're all fixed at 1, whereas the factor loadings from the slope factor to the repeated measurements, you have fixed values of 0, 1, 2, and 3. And basically, by virtue of this coding right here with the 0 on this first as the first loading, what this is going to mean is that the interpretation of the intercept will be the predicted level of customer service at time, well, basically the first time point or first measurement occasion. Now, you'll notice that over here we have D1. This is basically the gender variable that we're working from. And you'll notice that gender is basically predicting variations in slopes and intercepts. And so what we're trying to do essentially is we're trying to model variation in the individuals, the customers' initial levels of satisfaction, which is reflected by the intercepts, as well as their growth trajectories, which is reflected by the latent slope factor. And so we're going to be using gender as predictors of variation in the initial status as well as the growth rates. Now, by virtue of including the predictor gender to slope and intercept, now both of these have error terms that are given right here. So these are disturbance terms. And then you'll notice the double-headed arrows indicating that we are allowing those disturbances to covary. Now, on the right, you'll see we have the computer output. And it's basically, as I was mentioning, there's an error. So really the output that's given is not actually correct in the textbook. So let me show you why that is the case. So on the left over here, you'll see that this is the code that they gave us in the book and also in supplementary materials. And you'll notice, first off, just briefly, the install packages function. So this is, if you don't have Latent already installed, you're going to need to do it. So you can use the install.packages function, and inside the parenthesis, we have single quotes and then Latent. And so this is basically going to call up the Latent package for installation. So once you've installed the package, you will need to call it up to use it. So just because you have a package installed doesn't mean it's ready to use. So we're going to use the library function to call up the Latent package and then run the analysis. So in the code that was given, you'll see first off over here we have satisfy, and this is basically just the name of a data object that's going to contain the model information. So it says satisfy equals, and then you have a single quotation mark right here. So the equals is just basically designating that everything to the right is going to be saved in the satisfy object, and basically we start the model information with that single quote, and then we end it with a single quote as well. So don't forget that. You have to basically close it out. I typically, instead of using equals, I typically will just use an arrow, which is just simply the a less than sign followed by a hyphen. Now, on the next line right here, we have a pound sign and intercept. You also see a pound sign here in slope, and then pound sign and regression right here. So the pound sign is indicating essentially a comment. So this is just, this first one up here is indicating that we are going to be modeling the intercept factor. So to do this, they're just using the using an I to stand for the intercept factor. So in Lavaan, when you are specifying indicators of a latent factor, you're going to have the factor name to the left, followed by an equal sign and then a tilde sign. And then on the right, you have the names of the indicators of that factor. So you'll see that we have Y1, Y2, Y3, and Y4. And this is how the repeated measurements are appearing in the actual data set. You'll notice too that we have 1 times Y1, 1 times Y2, 1 times Y3, and 1 times Y4, and each of these are separated by plus signs. So next, underneath the slope comment, you'll notice that we're designating a slope factor, or naming a slope factor, and then we have equals followed by a tilde sign. Then again, Y1, Y2, Y3, and Y4. But in this case, we're fixing the regression slopes for time 1 at 0, for time 2 at 1, time 3 is 2, and then time 4 is set at 3. Now, you'll notice that with the regression right here, this is where the error comes in. And so what they have right here, you'll see it's got a I plus S right there, and this part is fine, and this part is actually fine too. But where there's the error is this part right here, where it's got an equal sign followed by a tilde. As I noted above, the equal sign followed by a tilde is used to designate indicators of a latent factor, and in this case right here, the way this is specified, you're actually using gender, or treating gender as an indicator of both the intercept and the slope, which is incorrect. So really that equal sign should not have been there, and you should have just had the tilde sign, and that would designate or indicate that you have a regression of gender on basically a regression where gender is predicting the intercepts and the slopes. Down here you've got model fit. This is essentially a new object that's being created in R. You'll see it says equals, and so what we're using is the growth function. So this is telling the Lavaan package that we're going to be doing a growth curve model. So we're using the growth function, and inside the parenthesis we're referring to the satisfy object that contains all of our model specification, followed by a comma, and then data equals satisfied. Basically, you have, this is a data argument equals, and then this is the name of the data frame that contains the data for our analysis. Then down below we've got summary function, and inside the parenthesis the name of our fit object that contains all of our information when we run our analysis. So again, this is the output from the textbook, and what I wanted to do really quickly is just show you, this is where I kind of worked up the model. This was actually before I looked at their syntax. There was something a little odd or seemed off when I was running the analysis before and comparing it to the book, and that's kind of what led me down the road of finding out that little syntax error. So this is my specification, and so I'm just calling the data object, the object containing the model specification. I'm just calling it model. It's basically arbitrary. Previously, they used specify, or they used the satisfy name, and I'm just using model right here. You'll notice also I'm using an arrow instead of an equal sign. That's fine. I have my single apostrophe here, and then at the end right here we have to close out our model specification with that end apostrophe. So you'll notice that instead of using I'm just typing in intercept followed by an equal sign and then a tilde sign. Then we have 1 times y1 plus 1 times y2 plus 1 times y3 plus 1 times y4. And then I'm creating the slope factor. I have my equal sign and tilde. Then 0 times y1 plus 1 times y2 plus 2 times y3 plus 3 times y4. You'll notice that I've added a comment line right here. And instead of writing out intercept plus slope followed by a tilde sign and then gender, I just created separate lines, and this works fine. This is actually just kind of helps me to keep things in order. So I have intercept followed by a tilde sign, then gender, and then slope followed by a tilde sign, and then gender. And then basically all of this is laid out very similarly as we had before. I named the fit object fit, and then followed by the arrow, and then growth, and inside the parenthesis model, which is a reference to the object containing the model information. Again, there's data equals satisfied, summary, and fit right here. So basically the name of this object is being put right here. I have a comma, and then I like to ask for fit indices. So I'm going to request fit, use the argument fit.measures, and set that equal to true. So I've got R opened up, and let me just kind of note, here's the text file right here that I'm working from. I do want to mention that if you go to this link right here, there's a little tutorial on latent growth models using the Latent package. And you'll notice that right here, this is just asking to take a quick look at the structure of the data. So str is for structure, and let's just take a look at it. We'll type in str, and then inside the parenthesis, I'll type in satisfied, which is the name of my data frame, and hit enter. And so now you can see, this is a data frame. There are 35 observations, basically 35 individuals who responded to the satisfaction measure, and then there's 6 variables. So we have a participant identifier. We've got y1, y2, y3, and y4, which I've already talked about, and then the gender variable. Again, 0 is coded for female and 1 is coded for male. So in the interest of time, I'm actually just going to copy this out of my syntax file. It's basically in a notepad, a text file right here, and paste it into R. And that certainly helps to kind of alleviate problems with respect to syntax errors. So now, as we're looking at this, you'll notice that first off, at the top, we've got a model test, and then we got various fit indices. So up here we have a chi-square goodness of fit test. So there's the chi-square value, degrees of freedom for the model, and then a p-value. And so generally speaking, a non-significant chi-square value would be taken as an indicator of good model fit. And so that's an indication right here that our model seems to be exhibiting good fit. Just let me note that that the chi-square test is impacted by sample size, and so typically we rely on other indices. We place a little bit less weight on the chi-square test than perhaps we used to. So other indices that we would use include the comparative fit index and the Tucker-Lewis index. So both of these values are roughly 0.98, both of these, and values that are 0.95 or above are generally considered indicative of a very good fitting model. Values above 0.90 are generally considered acceptable. So both of these are indicating a good model fit. Then you can see that we have the root mean square error of approximation that's given right here. Values that are at or below 0.05 would be considered indicative of a close model fit. Values that are 0.08 or below are generally considered acceptable. So based on that, we have evidence that the model has an acceptable fit to the data. We also have the standardized root mean square residual, the SRMR. It's 0.077, which is a little bit on the high side. Values that are around 0.05 or below are generally considered indicative of good fit. So as we scroll down, you also see that we have our where we've specified our factor model and the fixed factor coefficient. So you'll notice that we have the intercept factor y1, y2, y3, and y4, and all of these are fixed at 1. Those are the factor loadings. Then slope factor, there's our tilde equal sign and a tilde there, y1, y2, y3, y4, and you can see that those values are fixed at 0 through 3. So next, we'll scroll down, and you'll notice that we have under intercepts right here, we've got intercept and slope. So these are our latent growth factors. So the intercept value that you see right here of 1.549, because gender was included as a predictor of variation in the intercepts, and females were coded 0, then basically this would be the predicted time 1 value for females. So the time 1, the predicted time 1 customer service for females would be 1.549. The slope is also being predicted by the gender factor, and so in this case right here, this would be the predicted slope for females. So, you know, in a nutshell, for each increment beyond the initial status, time increment beyond the initial status, we would predict an increase in the customer service or customer satisfaction of 1.309. Now, down below, you'll also see that we have variance estimates. So we have variance estimates for each of our repeated factors. So this is basically residuals, residual variances associated with those. Then we also have a variance estimate concerning the variation in intercepts and slopes, and both of these are statistically significant. Now, if we look at the regressions, and this is what the piece of the output that I was talking about that was missing from the chapter, you'll see that we have intercept followed by the tilde and then gender. And so basically this is the intercept being predicted by gender. So the slope that you see right here, the negative 0.349, is the difference between males and females with respect to their initial status. So recall that females' initial status was predicted to be 1.549. So if we take that number and essentially add it to the slope, which is actually negative, in that case, that would mean that males would have a lower predicted initial status with respect to customer satisfaction than females. With respect to the second regression slope, again, this is the predicted slope for females right here, and you can see that the slope for males would have to be lower than the slope for females. So in other words, the positive gains over time for males is going to be less than the positive gains over time in terms of satisfaction with respect to females. Then getting back to that little piece I was telling you about with the covariances between the disturbances for intercept and slope, this is it right here. And you can see that there's no significant covariation between the disturbances for the intercept and slope parameters. So one last thing before I wrap this up. I did actually rerun the analysis using SPSS. I essentially used the multi-level regression modeling or mixed models approach in SPSS, and so I was able to generate predicted values with respect to customer satisfaction over time for males and females. And so you can see right here that I've just basically plotted the predicted satisfaction levels for males and females across a time period. So this is basically time 1 right here, time 2 right here, time 3 right here, and time 4 right here. And so you can see the blue is essentially for females, and the ones are for males. And you can see right here that males at time 1 were predicted to score lower in terms of satisfaction relative to females, and also the growth trajectory for males was weaker than it was for females. So that pretty well concludes the general analysis. Let me just reiterate again, this is the original code that was provided by the authors for Chapter 14. And again, this is the error that I was telling you about. And if you wanted to demonstrate that essentially we were using gender as an indicator of both the intercept and slope factors, you could reparameterize the model in this way down here. This is just me redoing it, but adding in gender as an indicator of I, and also the slope factor. And what you'll find if you run that analysis is that you'll get exactly the same coefficients and fit and everything. And actually I provide demonstrations of the output using the two syntaxes in the PowerPoint. So be sure to check that out. So that concludes this demonstration, and I appreciate you watching.